Okay, so let's talk about the third application of Gauss law. Here we are going to find electric field strength due to charged sphere. This charged sphere is not a hollow sphere, so that means it is completely filled, and consider it to be non-conducting, in which the charges are uniformly distributed. So there will be two cases for this particular application. So one, we will be finding the electric field strength outside this charged sphere. So here we can consider at this P point we will try to find electric field strength due to this charged sphere. So basically what we are going to do, so as we know we are going to apply Gauss law, so we are going to consider a Gaussian surface, so which will uh, enclose this charged sphere. And we, since we are finding the electric field strength at P, so therefore we will take the radius as a small r, the distance from the center of the sphere to the point P, and then we are going to draw our Gaussian surface. Here the Gaussian surface will be spherical, so which will enclose this sphere of radius, which is given by capital R. So outside the sphere, so basically what we are saying, our R in this case will be greater than the radius of this sphere. Okay, so using the concept of continuous charge distribution, let us first see how much charge is enclosed by this Gaussian surface. Okay, so since this is a sphere which will have volume, and entire volume the charges are uniformly distributed. So then we will use the concept of volume charge density, volume charge density, which is given by rho. Okay, so then volume charge density is defined as uh, derivative of charge with respect to volume, or in other case, how much charge is present in this particular volume. If I make dq as subject, so then rho dv, I can write this in this way. If I integrate for the entire sphere, so then dq will be q, and it will be rho. Rho cannot, we should not integrate rho, it is constant. So volume will be v. Okay, so what are we actually finding? So we are finding how much charge is enclosed by this Gaussian surface. So I will write charge enclosed, and rho is the charge density, or how much charge present per unit volume in this sphere, and V will be the volume in which the charge is present. So therefore, the charge is present in this volume of this sphere, which is capital R. So rest of the space, the charge is not present. So we will only consider the volume in which the charge is present. So in that case, the volume of the sphere is given by 4 by 3 pi, and it will be capital R cube, because the charges are distributed in entire this volume, which is, and the radius of this sphere is R. So now we have how much charge is enclosed by this Gaussian surface. So let us make it as equation number 1. Okay, so now let's find flux through this surface. Okay, flux through the surface. So you know this, since there's a ball or a sphere of positive charge, so it is going to give the electric field in all the directions. So we will consider a small surface in this Gaussian area here. So we'll consider this as ds, and then you know the surface area vector will be perpendicular to the surface like this. So this will be the area vector for the surface ds, and you also know that the electric field will also be perpendicular to the surface. Okay, so let me draw again. So again, the electric field will also be in the same direction. So electric field will also be perpendicular to the surface or parallel to this area vector. So then you can consider the small surface area anywhere you like, and every time you are going to get the same result. So here also, if I consider this, then surface area will also be perpendicular to this sphere, and then the electric field line will also be perpendicular to this surface. So but right now we are just talking about this ds surface area, which we have considered at P, where we want to find the electric field strength. So then d phi out there, So the flux at that particular, okay, this is true, d phi out there will be simply E ds cos theta. So where theta is the angle between electric field strength and the area vector. So since this Gaussian surface will only have one surface because it's a sphere, so then we only have to consider that particular surface. Okay, so then theta is already previously we have understood and we know that it is okay. It is an angle between electric field strength and area vector. In this case, theta equals 0 degree. So which if you use in the above equation, so d phi you will get E ds. So if you integrate above equation, if you integrate above equation, or you can integrate above equation to get total flux, total flux. So then the integration of d phi will be phi, and the integration of ds will be s. And here, what is s? Here, what is s? S is the surface area of the Gaussian surface, and it's a sphere, and it is given by 4 pi small r squared, because small r is the radius of the Gaussian surface. Okay, so then if you use that into the flux equation, what I'll get? I'll get E 4 times pi r squared. So you should remember the surface which we are integrating is the Gaussian surface, so whose radius is r. So small r basically. So then that is the reason that I have written small r out here. And number two, now finally apply Gauss law. Applying Gauss law, what we are going to get? So Gauss law says phi is q enclosed time epsilon naught. Okay, q enclosed times 1 by epsilon naught, and q enclosed is basically the charges which is enclosed by the Gaussian surface, which we have already derived. So then we will use that equation here. So it will be a rho 4 pi r cube divided by 3 epsilon naught. So equation 3. So now compare equation 2 and 3. So compare equation 2 and 3. So both is for flux. We are trying to derive electric field strength. So then comparing 2 and 3, what we are going to get? We are going to get E 4 pi small r squared equals to rho 4 pi capital R cube divided by 3 epsilon. So 4 and 4 will cancel out, pi and pi also will also cancel out. So if I make E as a subject, so here I will write, so E will basically be your rho r cube by 3 epsilon naught r squared. Okay, so give this as equation number 4, and this will be the, so this will be the electric field strength outside the sphere, outside the charge sphere here. Okay, so then now let's do it for the other case, that is inside the charge sphere. Now let's do it for the second case, that is inside the sphere. So inside the sphere you can consider any point inside the sphere. Here I have considered P point out here. So that is basically given by small r. Okay, and again, like previous case, the capital R is the radius of this charged sphere, and in this case here it is clearly mentioned that small r is less than capital R. Is of course is obvious that since the point is inside the sphere where we have made a Gaussian surface, so the yellow sphere which you see, the Gaussian surface that we have observed. Okay, so then now one thing is here. So since our Gaussian surface has decreased, so the charges which will be enclosed by this surface will also be increased, and the volume of the Gaussian surface, or the in which the charge is present, will also be decreased. But the charge density will remain same because we are talking about the same sphere. So density is a constant; it will remain same. So here what we can do, we again have to derive charge enclosed by the Gaussian surface. Okay, charge enclosed enclosed by the Gaussian surface, and that will be, so now see, since the rho is not going to change. Okay, charge density, we'll again going to use volume charge density. Volume charge density is given by rho, and rho is again uh, dq by dv. Since q and v symbol we have already used, now you know there are lesser number of charge enclosed by this volume, so I will use a new symbol, that is q dash, and v dash is the changed volume. So then if I make q dash as a new volume, a new charge which is enclosed by the volume, so it can be rho as rho v dash. So if you integrate, I'm going to get q dash is equal to rho v dash. Now tell me what is v dash. V dash is the volume, but the volume of the Gaussian surface which encloses the charge. So now the entire charges are not enclosed. Only the charge which is present in 4 by 3 pi small r cube is the charge which is enclosed. So therefore, now I can write new charge enclosed will be rho times 4 pi small r cube by 3. Okay, so this will be your equation 1. So now let's do the same thing. Let's find the flux. Okay, so flux through the sphere, through the surface of a sphere of the Gaussian surface. So then I will again consider a small surface in this Gaussian surface. You will see the electric field will be directed in this direction. So electric field will be directed in this direction, and similarly the area vector will also be directed in the same direction. So here this will be electric field and this will be direction. Again theta in this case will also be 0 degree. So the phi will d phi, if I talk about, it will be e ds cos theta. Theta is 0 again, so it will be d phi is equals to e ds, and okay, after integration, so phi will be es. But what is the surface? So now this surface is the surface area of the new Gaussian surface. So S in this case will be 4 pi small r squared, because which surface we are talking about? We are talking about this surface of the Gaussian surface. Okay, so which is enclosing the charge. We are not interested in the surface, entire surface. We are only interested in the Gaussian surface. So then I can write phi equals e 4 pi r squared. So now this will be my equation number 2, and now finally you can use the Gauss law. Applying Gauss law. After applying Gauss law, you can write phi is equal to q dash, because new charge which is enclosed is q dash, and times 1 by epsilon naught, which will give you, we already have how much charge is enclosed is 4 by small r cube by 3 epsilon naught. Okay, so by using the q dash from equation number 1. Okay, so this will be our phi. We can give it as equation number 3. Now you can, okay, so you can compare equation 2 and 3. I'm going to use this small space which is here. Okay, so comparing equation 2 and 3. Comparing equation 2 and 3, what I'm going to get, e 4 pi r squared equals rho 4 pi small r cube divided by 3 epsilon naught. So r squared, if you cancel with this cube, so only one r remains. 4 cancel with this 4, pi cancel with this pi. So E basically is your rho r by 3 epsilon naught. So it is equation number 4. See, this is the electric field strength inside the sphere. Okay, so now the most important part. So let's interpret both the equations. So how much inside we have found? We have found it to be rho r by 3 epsilon naught. And how much outside? I have found this rho r cube by 3 epsilon naught r squared. So let me check once. Okay, so see, rho r cubed by 3 epsilon naught r squared, and yes. Okay, so if you see inside, the electric field strength is going to increase if you increase a small r. So what does that mean? So let me show you why it happens. As when you are inside the sphere, and when you are inside the sphere, when you increase r, you are going to enclose more charges. When you increase r, you are going to enclose more charges. If you enclose more charges, the more charges will produce more fields, and if there are more fields, then there will be more field strength. So therefore, inside the charge, when you increase r slowly, the electric field strength is going to increase. So therefore, you see inside electric field strength is directly proportional to r. But once you reach the surface, when small r and capital R will be equal, so that means the small r will be equal to the radius of this sphere. If you increase further, then you will get to the first case. Then you will get to the outside the sphere. Now you do not include more charges or enclose more charges, but you just go far and far from the charge. And since you are going far from the charge, the field strength is going to decrease. So therefore, the electric field strength outside is inversely proportional to the small r. So the small r is a variable here, since it is changing from, it is starting from 0, it is increasing, it is enclosing more charge and more charge, the greater the field strength. So once it reaches the surface, now it cannot enclose more charge. But if you go further and if you increase r, then you go away from the charge. And then the field strength becomes inversely proportional to r. That means the field strength is going to decrease. So then if you have to show that with the help of a graph, so this portion out here, the r is increasing from 0, and then it is reaching the radius of the sphere. After that, it is going outside the sphere. Okay, so inside the sphere, it is directly proportional. So that means you will get a linear graph like this. If you increase r, so e will also increase. But as it goes outside, or once it reaches the surface, if you increase r further, then it is going to be inversely proportional. So therefore, it is going to decrease, and the inversely proportional graph is made somewhat like this. So this is how you can show the variation of electric field strength with distance r. Okay.